Get over here. All right. Last time we ended with the idea of a unit vector. And a unit vector, remember, a vector has magnitude and direction. A unit vector is a way to kind of isolate the direction off of that vector without the magnitude. It does have a magnitude of 1. So a unit vector is a vector. It just has a magnitude of 1. And you're going to see that's convenient. Also, at least y'all need to take linear algebra. And vectors are very, very important in linear algebra. They are, and I mentioned before, you can make vectors out of any number of things. You can create things that behave like vectors, or matrices, that are functions, that are, or derivatives and integrals can become vectors. So anyway, we showed that little result. Let's do this right here. Okay. Standard unit vectors. And this has its 3-dimensional counterpart. Standard unit vectors, we have these things called I and J. And what they are is they're unit vectors parallel to the 2 coordinate axes. Okay. So let's go up here. If I have the coordinate axes, the unit vector in the x direction is called I. The unit vector in the y direction is called j. So j is 0, 1, and that is the terminal point, 0, 1. And when you denote a vector, you always put the angle braces on, right? You don't do the rounded braces is if you're denoting a point. So we can express, this is very important here, we're going to be doing a lot of this. You can express any vector as a linear combination. Linear combination, that's a new word. As a linear combination of those 2 component vectors. And so let me see here. We need an example here. Why do we not have an example? We need a big fat example right here. So you have, suppose you have the vector v. Let's do here. V equals 2 minus 3. And to follow what's being done here, is we can write that as a linear combination of I and j. Right? And so this equals 2 times that plus, I'll tell you what, let me back up and make it a little simpler. That equals that. And I'm not going to go into such detail usually. And then this 2, 0 is nothing but what? 2 times 1, 0. Right? And then minus 3 times 0, 1. I need to add this example for next semester. By the way, if there's little tweaks you think would be helpful for you to learn out of these slides, if I organized something different, if I added a slide, if I took a slide and broke it up into 2 slides, that's a big one I've done a lot of. I tend to try to cram too much on one slide. That's not all I've gotten better at it, but a lot of things just get broken up into 2 slides. Let me know how these slides can be more useful to you. And you might say, wow, that's not me. What the next guys? Well, number 1, you've been helped by your previous peeps. Secondly, I got 4 more We got 4 more chapters with the slides to do. So maybe that concept can be used in future chapters that we take here. I appreciate it. So anyway, so this is nothing but 2 I minus 3j. So this right here is this is what's meant by a linear combination. A linear combination. And then they make the distinction that V1 and V2. This is the vertical component. That's the vertical component. That's the horizontal component. No, the other way around. That's the horizontal component. That's the vertical component. So that just is some nomenclature for us. Another thing we could do is, well, really me. I told you that before. I'll be in meetings. I told you. I'll be in meetings. Not to Dr. Marcello. Mark, what are you thinking back there? I'm not going. If I don't get something, I'm like, why are we doing this? Sometimes what I'm putting on my face is not necessarily a positive thing. That's the problem. I'm like, I've gotten to be more poker faced. When something really stupid gets announced, I just sit there. I'm good at that. It's when I'm really trying to figure it out that if we have a unit vector, polar coordinates, where to get to the corner of the room back there, I can go in the I direction so many steps. I can go in the J direction so many steps and get to the corner. I can also go turn to that corner at a certain angle and walk straight. That's the decimal. That's kind of what we're saying here. But a unit vector, now we're talking about a unit vector. In fact, I probably should underline it. A unit vector. If it's a unit vector, then whatever's in front of the I and whatever's in front of the J are the cosine and sine. So if it's a unit vector in the direction of some vector v, if you make a unit vector in that direction, what's in front of the I and j are the cosine and sine of the angle that vector makes with the positive x-axis, right here. Okay? Because a unit vector is going to be on the unit circle if you put its tail to origin. And so, by definition, the x-coordinate is the cosine of something in the unit circle, and the y-coordinate is the sine. So this is the x-coordinate, basically, and that's the y-coordinate. Homework. Now this is out of the book. I probably ought to do this more. It's just out of the book. But anyway, those you have the answers to, so that's some fun for next time. As usual, the stuff I assign in class is not adequate to prepare you. If any of this, if something gives you a little bit of trouble, challenged on it, do some more problems like that. And of course, come to me. Yeah. Does anybody ever have a spark money? I haven't heard. Is on for money?
Are you going to be there?
Yes, yes. That's right. I got the spark lady here. That's awesome. I told you. I'm at all.
I mean, I put you on the list. So
Good. I'm at all. Is there going to be a spreadsheet come out for that?
Yes. I was kind of waiting until I
you
after
did
the first one.
Right. Yeah, no problem. No problem. Yep. I am there.
I also already just put you in for every single one of them. So.
I try to do that. I try to be there for them. Yeah. And I will say, I'm an old man, so 8 to 9 is when you catch me. Don't show up. If anybody shows up, 9:45. Although I've been there to 10 and after 10 a couple of times.
I know. I've been there with you until then.
So I'll stay there until students are done, and I'll do that better. I just don't. I'm not going to wait around for 2 hours for someone to show up at 9:45. I was kind of a little bit vocal with regarding coaches. You got a student struggling. I'm sorry, them being at your tutoring session is more important than your team meeting. I'm sorry, that's my opinion. I'm from the academic side of things. I'm not from the athletic side. But you got somebody who's at risk of failing a class or whatever, they're in trouble. When you're half your team's that way, get their butts to spark, right? That's just where I'm at.
In fact,
What?
I'm going to try and partner with some of the coaches so that won't happen.
Right.
So, we'll see.
Good. Yeah, we're good. I really appreciate it. So, we had science people doing this before. We had Carter last year. And then, of course, we Lydia before that. But that's good. Good. Anyway, totally forgot. Spark. You add spark, right? So, literally, she's adding spark. Okay. Vectors of space. Now, this is just the three-dimensional version of what we just did. And I'm going to blow through a lot of this. Like, for example, this right here. This. IJ, guess what we can do? We can do IJ and K, right? We can do, right? If this is x-axis, y-axis, z-axis, right? We can do I, J, K. And so on. This goes on to other dimensions, right? So a lot of what 11.2 is nothing but the three-dimensional version of 11.1. All right? So I'm gonna blow through a little quicker. Okay, this is a nice, neat version of what I just drew. But the z-axis traditionally is up and down, and x and y are flattened out. So if you're used to the x and y axis being like this, the z-axis is kind of the one going up and down instead of the y-axis. All right. All right. So we have what? Names of planes. The xy plane is now flat. I wish they'd use different colors. Why can't they put a blue or something? This one here is the xy plane. And then we have the YZ plane. Now, along the XY plane, Z is 0. Just like along the x-axis, Y is 0. Along the XY plane, on the XY plane, Z is 0. On the XZ plane, Y is 0, and so on. Right? And so we label stuff X, Y, Z. Right? That's just the order, right? And this can go on other dimensions too. You're going to be drawing a lot of this semester. More of it than you want. This chapter especially. Well, no, I'm lying. All the chapters. But I would say this and chapter 14 are the most intensive in drawing three-dimensional things. Another thing, look here, the distance formula. The distance formula is you just have the z's tacked on. The one you've seen all your life, that's been your distance formula for x, y. Right? You take the difference in the z components of square, and that gives you the distance from one to the other. And that's how you're going to get the magnitude. That's how you're going to get the magnitude of a vector, is that if you put its tail at the origin, right? One end of it's a bunch of zeros, the other end is the sum of the squares with the square root. We're going to start getting into different three-dimensional shapes. The most basic is a sphere. Because you remembered a circle? In fact, we do this. We did in chapter 10. Yeah, we did parabolas and sphere and hyperbola and all that. That, by the way, that was not a great chapter to have to do online. We did. And we got through almost all we needed to get through too, which is good. So if we had that, just that much, with that and that is your circle of radius r. And so we put a z component, which is sphere radius r, where the center is x, y, x0, y0, z0. Midpoint formula. these are direct extensions of what you have in 2 dimensions. That would be the midpoint of the line segment in the XY plane. You just average the components. So here, find the equation of a sphere with that center and with this radius. Right? And I'll make sure we're going. I'll make sure something's not on the next page. Find the equation of the sphere with that center. Well, this is our x0, y0, z0. And this is our r. I have an R in speech. I really do. I have math in the real world. It took me years to learn to say parallel. I did that pretty good now. It's bad for a math teacher when you can't say parallel. So this is our form right here. Right, that's our form. So we down here. And we plug. X, Y, and Z don't get plugged in for. Those are going to remain in our final answer, right? So you're going to have X minus the X component, which is 1, plus Y minus the Y component, plus Z minus the Z component, equals the radius squared. And that is just going to be x minus 1 squared plus y minus 5 squared plus z minus 6 squared equal 2. Now, we did do some stuff like this last chapter 10. This you can read off a lot of useful information, but sometimes you're going to see this stuff expanding. And we did that. We're going to see stuff like this. I'm only going to do this once because the later section of chapter 11 uses this, but you can expand that into that. Then right? And then you can combine these, you can combine those constants. And so you will see this sometimes written like this. Now, 1 plus 25 is 26. Did I screw something up?
Why does it equal 4?
That's a really good question. That's an excellent question, Emily.
Why could be a distance?
I need a second cup of coffee or something. Yeah, as always, don't hesitate. So 26 plus 36 is 62. So when you subtract 62 from that side, this sometimes is called the general form. And so if you're given something like that, and we did some of these for hyperbola and stuff, but there were only 2 dimensions. We're doing the 3-dimensional one this chapter. To go back from here to here, you have to complete the square. We're going to do that later. Always a problem. Right? So vectors in space, 3-dimensional version, right? So you have u equals u1, u2, u3. That u here is not a unit vector. We were using u as an example unit vector 5 slides ago, right? U is just a vector with U1, U2, and U3 as its components, and there's V. Vectors are equal if their components are equal, duh, right? Component form, if V is represented by a line segment from this to this, how do I get the component form? I subtract the endpoints in the same order. So, for example, Q is my terminal point, so I have to subtract P's from Q's, right? This is the endpoint, this is the initial point. So I subtract P's from Q's, and each of these three things are just numbers now inside angle braces, angle brackets. Length, that's the same thing we had last section, right? 2 dimensions, 3 dimensions. Unit vector, that's identical. There's nothing different about that at all. Oh, I guess except that V3 right there. We had V1, V2, but you take a vector, divide by its magnitude, it always comes out to be a unit vector. No matter how many UV, X, Y, C, P, Q, whatever, however many components. Vector addition, you add vectors by adding component-wise. You add the first components, add the second components, add the third. We're going to be doing a lot of that. Scalar multiplication, scalar, for some reason in vector speak, scalar we call ordinary numbers on the number line, we call scalars. So a scalar is just a real number. Times a vector is that scalar times each component. Right? Parallel vectors, if one is a scalar multiple of the other. So if you can get one vector by multiplying another vector by any non-zero number, right, then they are parallel. So for example, obviously this vector and a vector in the same direction only this long would be parallel. Some multiple of one would be the other. This vector and that vector would be parallel. So I can multiply this one by some negative multiple of that. And so here's a little drawing that they have in the book. Right? It does, so you have to get through your head that a vector pointing quote unquote the other direction is still parallel to, because you can multiply that by a negative number and get that. Right? So parallel. All right. Are the following vectors parallel? So you'd go 4 times, what do I have to multiply 4 by to get minus 2? Minus 1/2 is minus 2. Minus 2 times minus 1/2 is positive 1. 6 times minus 1/2 is minus 3. Now these, as you probably have already caught on, are the same. Okay? So if this is U and this is V, U is 2V. And since one can be written as a scalar multiple of one another, they are parallel. Are the following parallel? What do you reckon the answer here is going to be? Right? So 1 times 4 is the 4. 2 times, what would that be? Minus 3/2 equals minus 3. And you see right away, these are not the same. So I have to multiply the 2 by a different number to get minus 3 than I do the 1 to get a 4. And the 10 and the 7 similar, right? So you'd have 10 times 7/10 is 7. So you see those 3 aren't the same. And if any 2 of them were the same, but the third one was different, even if 2 of them were the same, I should make the problem now. the answer would still be no. Now, just to give you an idea, I'll try to, long time ago, I used to have a table here all the time. And then what happens, somebody stole the table. And then you know that table has now turned up. That table now turned up. And the last time I saw it was in Campbell. Yeah. So anyway, okay. So these two vectors, let's suppose these two vectors here. These two vectors here are parallel. Right? And so if you put them, one would kind of be on top of the other, maybe a different length. But these two here are different lengths. Those two are parallel. Now suppose I change just one component of one. What that's going to do is going to tilt it away. Right? It's going to tilt it away, right? In one direction or the other. So if you change the z component of the arrow, it would say I made it bigger, it would tilt it up in the z direction. Same way. Right? If I changed another component as well as the z component, it would say the y one, it would move it that way. So you're moving it away, changing components. So when you change the multiple, they don't have to be identical to be parallel. We're going to get more into this. Okay. What?
Why is it the same thing? It's a lot more.
Yeah, there you go. There you go. This is not so involved. It's going to get more involved. Now we talked about adding and subtracting vectors. Now we're going to talk about multiplying. There are two ways to multiply vectors. One's called the dot product, which we're going to do first, and it's easy. The other is called the cross product, and it's a little more complicated. Right? The dot product, before you even know what they are, the dot product of two vectors is a number, whereas the cross product of two vectors is another vector. Now we expect, this is different. So we expect if you combine, you take an operation plus or minus or divide, you combine two numbers, you get another one of the same thing. No. You don't combine two numbers and get a frog. Only it can. I have a lot of frogs this year. So here we're combining with the dot product, which you're starting off with, which is the easier one. You combine two things, and we're actually going to get another number. So we're combining two vectors, and we're getting something of a different type. It's pretty easy, though. All right. If I have two vectors u and v, and here's the three-dimensional version, right? U and v with 3. You multiply their first components together, second components together, third components together, add them up. Now remember, there's no i's, j's, or k's over here. That's why you get a number. So, let's go. U dot v is what? Multiply the I'm going to call it the x, the first component, the x component together. Minus 1 times 2. The y component together, 0 times minus 1. The z component together, 5 times 1. And that gives me minus 2 minus plus 5 is 3. So 3 is our dot product. All right? Our dot product. All right? Properties of the dot product. Most of these are going to be straightforward. And I'll try to give you a little insight there. U dot v equals v dot u. It's commutative. Well, that makes sense because if I just drew a squiggly line here, this is u dot v. I could rearrange these numbers. You see these numbers here? I could rearrange them into 2 times minus 1 plus minus 1 times 0 plus 5 times minus 1. In other words, I could, since multiplication is commutative, I could flip the order of each of these, right? And I wind up with v dot u.
That was easy.
Okay. You can distribute the dot product over a sum. So if this was the number, don't write this down. If that was the number 4, I could distribute the 4 across those two. Right? For the dot product, that works as well. So u dot v plus w is u dot v plus u dot w. Now, we could get into proving these things by saying, let u equal brackets u1, u2, v3. Let v equals u1, v2, v3. Let w equal w1, w2, w3. And we could actually compute what that is, rearrange those terms algebraically, and get that. We could do it. Where am I going? Lazy bottom. Well, here's the number. The number across a dot product, a little different. It doesn't distribute. So this u got distributed to both of those components, whereas the constant only goes to one or the other. If you were to put another c here, don't write this down. I'm going to erase it. If you put another c here, that would be c squared. The 0 vector dotted with any is 0. That should be evident because you're going to have all zeros. Here you had 1 0, right? But if you had all zeros, 0 there, 0 there, and 0 there, you're going to have zeros. And this one's a little bit funkier. But v dot v is that, right? That is and I'm only doing the 2-dimensional case. I can do 3 dimensions for this. This is and that equals get used to working with these components because you kind of feel like you're working in a different, I don't say different language, but certainly a different dialect, right? This is a good thing, but I was reminded of dialects in the United States listening to the political conventions. I didn't listen to all of them. But they both want to show themselves how diverse and so forth they are, the parties are. So they would have people on there giving their stories or whatever, their support from different parts of the country, different, I should say, different ethnic groups in the country. And even though it was English, in some cases it was like, I have to listen a little closer, So that, pay a little closer attention. That's kind of what it is here. This is a different dialect. All right. Oh, yeah. Yeah. Whoa. Angle between two vectors. Cosine of the angle between two vectors. If you put them tail to tail, the angle in between them, right, is cosine of that angle is the dot product divided by that. Now, how do you get that? Are any of you familiar with the law of cosines? Law of sines, have you ever heard of it? Well, the law of cosines is, how should I do this? A squared equals b squared plus c squared minus 2bc cosine of theta. And theta is the angle opposite, here, you want me to do? Sorry, not theta, alpha. How did that happen? Or alpha is the angle opposite A. Okay? So in this case, if I take two vectors u and v, this is the analytic geometry part of the class. I mentioned that in chapter 10. I always do. Where the last part of chapter 10 didn't have a lot of calculus. The hyperbola and directrix and foci of ellipses and stuff like that. That's the analytic geometry part. This is more analytic geometry, kind of trick. So if I have these any two vectors, u and v, okay, and I have theta between them. Subtract one for the other. I told you that the difference of two vectors was going to be across the tips of the vectors. It's that vector. So this is just a fundamental problem. Apply the law of cosines to it. Well, call this A and this alpha. Substitute that in here. And then call B equal to U and C equal to V. Okay? Uh-oh. Sorry. I didn't realize I had the whole thing on the next page. So what I'm going to do is redo that here. And so I start off with so relabeling that way. Let's see what we have here. We're gonna jump into some algebra here. All right. A is the length of the side opposite alpha. A is the length of the side opposite alpha. So the length of the side opposite theta is the magnitude of u minus v. So over here, I'm going to get the magnitude of u minus v is going to be, well, actually we have v minus u, right? That squared, right, equals b is u squared, the magnitude, plus c is the magnitude of v squared, plus u v cosine of theta. I know what you're thinking. Please. Okay. Right. So what I'm going to do is I'm going to expand this left side, this right side, I mean, and show that it's equal to that. We're going to expand this right here. And so this is what we want to get when we're done. Right? That's what we want to get when we're done. And so actually, you know what? What we have is this right here. UV cosine theta. I'm going to put that on one side and everything else on the other. So I'm going to put this on one. Oh, you know what? I have a 2 here. A 2 goes right there, and a 2 goes right there. Right? So I'm going to rearrange, and I get 2 that will equal this squared, and that's going to be what? What's that going to be? That's going to be V1 minus U1 squared plus V2 minus U2 squared plus V3 minus U3 squared. I'm going to move that down a little bit. I'll move that up. Okay. So I'm solving for 2UV cosine theta right there. Now I have to subtract these two. So that's going to be minus U1 squared minus U2 squared minus V1 squared minus V2 squared. Okay. This part right here equals minus that. This part right here equals minus that. Now I got to square these buzzards out. It's going to get ugly. Just keep it real. I'm going to put this equal sign over a little bit. Square that out. V1 squared minus 2V1 U1 plus U1 squared. Plus V. Oh, whoa, 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 whoa. I'm only doing 2 dimensions here. This right here, I don't need. Sorry. So I'm going to have V1 squared. It's V2 squared. Minus 2 V2 U2 plus U2 squared. Minus that stuff. Now we should have some cancel. So I have a V1 squared. Oh, I didn't catch it. Yeah, I'm only proving the two variables. But look here, V1 squared, V1 squared. V2 squared, V2 squared. U1 squared, U1 squared. U2 squared, U2 squared. We yabba dabba do, right? Because what I have left, this is 2 U B cosine theta. Now it equals minus 2. I don't like something. Hang on here. I'm getting negative signs where I don't want them. But anyway, that's going to be minus. I have a minus 2 there and a minus 2 there. So that's going to be V1 U1 plus V2 U2. I don't like that minus. Where do the minuses come from? I screwed up something up here. goes to the other side. Cross terms there are going to be negative. Because this here equals minus 2 times u dot v. U dot v. And so,
Oh, that's the whole place? I'm sorry.
yep. Couple more minutes. Right? Then I got that negative there. I'm gonna have to figure out where that negative comes from, but these twos cancel, right? And so u dot v is going to be, we have a negative to get rid of. I'm going to find out where that negative comes from. It's going to be u v cosine theta. We're out of time. I'm going to look at that right there, but that's our result right there. I'm going to have to look where this minus sign, that's the little minus sign. Do away. I don't want to keep it on. Right? Thank you guys.
Seems good.
Take care, Joseph.